Hey everyone, and welcome to This Explainer. Today we're diving into something absolutely wild, the absolute crucible that transforms a standard everyday commercial drone into an indestructible military-grade tactical asset. We're talking about an intense engineering gauntlet that is specifically designed to push both hardware and software right up to their absolute breaking points, and then push them even further. So, ask yourself this high-stakes question. What really separates a commercial toy from a tactical military asset? Because honestly, in today's heavily contested environments, an untested drone is really just a flying target. Sure, commercial off-the-shelf parts are cheap, and they're fast to develop, but they simply cannot survive the brutal, unforgiving realities of modern electronic warfare or extreme weather. For a drone to survive out there, it has to pass through a literal gauntlet of validation. Here's a quick roadmap of the crucible we're mapping out today. First up is basic reliability. Then we'll hit the environmental trials, navigate invisible warfare, look at NATO standards, trigger the fail-safes and last resorts, and finally, check out ground operations. Let's jump right in. Stage 1, the setup, focusing on reliability. Before a drone even gets near a simulated battlefield, it has to prove its worth against fundamental aviation standards. We're talking about establishing a baseline with standards like the RTCA DO-160 for airborne equipment. But the real test, that's how the system handles a sudden, catastrophic failure. To test this, engineers do something deliberately malicious called fault injection. Using hardware-in-the-loop simulations, they'll just intentionally cut power to a motor, instantly block the GPS signal, or simulate a massive battery spike. And here's the crazy part. The drone's brain, the flight controller, has exactly 1 single second to recognize that failure and trigger fault-tolerant control. It has to instantly switch to a backup system or enter a safe hover without crashing, literally 1 second to save its own life. Moving right along to Stage 2, environmental trials. Once the drone proves its brain can handle a sudden crisis, the physical torture begins. Welcome to the environmental trials governed by the infamous MIL STD 810H standards. This isn't just about baking a drone in an oven to see if it melts, it's about dynamic, multi-stressor testing tailored to actual missions. The abuse here is just incredibly varied. In the low-pressure altitude test, specifically method 500.6, they simulate the incredibly thin air at 6,500 meters, where cooling efficiency just completely plummets. They blast the drone with blowing rain and dust to test every single seal, and they'll even soak the whole thing in aviation fuel just to see if the composites degrade. Now, what's really fascinating here is the sheer violence of the thermal shock testing. They do not gently adjust the thermostat. They take the drone from a freezing minus 40 degrees Celsius and shove it straight into a blistering 75 degrees. And they often do this in under 60 seconds. This massive rapid thermal expansion and contraction, it's specifically engineered to crack composite materials and shear those tiny, critical solder joints right off the circuit boards. And if that wasn't enough, this thermal stress is compounded by mechanical stress in the sign-on random vibration test. You see, a drone doesn't just experience one simple type of shaking. This test perfectly replicates reality by stacking 2 stressors at once: the unpredictable random bumping caused by atmospheric weather and turbulence, layered directly on top of the relentless high-frequency sine wave vibration caused by the drone's own spinning rotors. It is a total recipe for structural fatigue. Next up is Stage 3, invisible warfare. If the physical chassis actually survives all that weather and shaking, it has to face a threat it can't even see. This invisible battlefield is governed by the MIL Standard 461G standards for electromagnetic compatibility. Modern warfare is highly electronic, right? A drone that leaks electromagnetic noise will end up jamming its own sensors or, way worse, act as a glowing beacon for enemy radar. So this invisible war is fought on 2 fronts. First is emissions control, that's CE102 and RE102. The drone has to be perfectly shielded so it doesn't emit high-frequency noise that drowns out its own faint GPS signals. Second is susceptibility, CS114 and RS103. Here, the drone gets blasted with up to 200 volts per meter of radio frequency energy to simulate hostile, high-power microwave weapons and radar beams. Through all of that, the motor controllers cannot glitch, and the signal absolutely cannot drop. But hey, human-made weapons aren't the only threat up there. The CS117 standard tests for indirect lightning strikes. If a drone is flying anywhere near a thunderstorm, a massive electromagnetic transient can surge right through its wiring. Without incredibly robust avionics protection, that surge will completely fry the microchips. instantly turning a highly advanced, super expensive tactical drone into a falling brick. Which brings us to stage 4, NATO standards. Passing those previous tests gets you close, but to fly alongside allied forces, you have to enter an elite club. We're talking about NATO airworthiness. Interoperability and absolute safety are just non-negotiable when you're sharing airspace with manned aircraft or operating over populated areas. NATO actually categorizes this rigorous testing based on the sheer physical mass of the drone. So, looking at the breakdown, Standard 4671 is for heavy drones, requiring deterministic safety. That means engineers actually have to mathematically prove the system has absolute fault tolerance. For lighter tactical drones under 150 kilograms, Standard 4703 applies, which focuses really heavily on mitigating the risk of a crash impact that exceeds 66 joules of energy. And part of achieving this NATO interoperability means surviving the human element on the ground too. Under the CS118 standard, the drone has to withstand a massive 15,000-volt electrostatic discharge from a human operator. Just think about the static shock you get from shuffling your feet across a carpet in winter, but magnified exponentially. Picture a soldier, charged with static electricity from running across a chaotic battlefield, grabbing the drone to load a weapon or swap a battery. The drone's semiconductors have to absorb that entire 15 kV shock without rebooting, glitching, or sustaining any damage whatsoever. Okay, stage 5, fail-safes and last resorts. This is where things get really dramatic. Because the crucial question is, what happens when the drone actually loses the fight? What if the damage is totally catastrophic and unrecoverable? That's where flight termination systems, or FTS, come into play. A compromised military drone just cannot be allowed to fly away into civilian airspace or dive into allied troops. So, when disaster strikes, the drone initiates the ASTM F3322 fail-safe sequence. It happens literally in the blink of an eye. First, it detects the failure. Second, lockdown. It completely severs power to the main motors in just 50 milliseconds. And third, within 200 milliseconds, it triggers a pyrotechnic or spring-loaded parachute ejection to bring the whole chassis down at a safe, controlled speed. And the engineering validation matrices required for this are just wild to look at. They are the literal receipts proving these split-second response times actually work in the real world. They mandate insanely strict requirements for simulating total power loss, triggering that 50 millisecond lockdown, and actively validating the 200 millisecond parachute deployment in real-world drop tests. There is no room for error here. But you might be wondering, how do they make sure that explosive parachute doesn't just deploy by accident mid-flight? Engineers use something called galvanic isolation. This physically and electrically severs the high-voltage motor circuits from the highly sensitive parachute trigger lines using optical or magnetic isolators. It acts like an electrical firebreak. This ensures that even if the main battery suffers a catastrophic short circuit and completely melts down, that massive transient current physically cannot jump over and accidentally fire the parachute while the drone is supposed to be flying normally. Finally, we reach stage 6, ground operations. This is the very last check before flight. Because let's be real, all the brilliant hardware engineering in the world is utterly useless if the human element fails on the ground. Strict operational protocols are the final, vital layer of this crucible. Before a tactical drone ever leaves the dirt, it has to be cleared for flight using standardized procedures like ISO 21384-3. Operators follow uncompromising go-no-go checklists. The drone must achieve a GNSRTK fixed satellite lock, which basically gives it an exact pinpoint position accurate to within 2 centimeters before the motors are even allowed to arm. And the whole shebang is governed by instructions for continued airworthiness to ensure the asset is maintained properly over its entire lifespan. As we wrap up this explainer, I really want to leave you with a core philosophy pulled straight from the engineering source material. Unverified design is just theory. A new drone concept might look absolutely fantastic on a computer screen, but until it is frozen, baked, violently shaken, electrocuted, and intentionally broken in this crucible of testing, it is nothing more than a theoretical concept. And that brings us to our final thought for you to ponder today. As warfare becomes increasingly reliant on autonomous systems, heavy electronic jamming, and fighting in extreme environments, in tomorrow's heavily contested battlefield, will your design actually survive the crucible? Thanks so much for joining me on this explainer. Keep questioning the engineering behind the technology we rely on, and I'll catch you next time.